here's Edgar Hammermeister.
Thank you very much. Well, good morning, everyone, and welcome to the show. I'm excited to be here to present to you this morning. Just before I get going with the presentation, I just want to ask a few questions of you. Who in the room buys and applies fertilizer? I do as a farmer. Who in the room sells or recommends fertilizer? I do as an agronomist. Who in the room is looking for a return on investment on that fertilizer? I hope we all are. So through my presentation here today, I'm going to be talking about, should we be focusing on maximum yield or trying to optimize our income? And in the latter part of the presentation, I'm going to be talking about some things that are happening in our soil with regards to the type of growing seasons or the weather systems that we've been having. So with our business of farming, even though our city cousins think that we've got a pretty good lifestyle, getting to work outside all the time, and for the grain farmers, we get to be inside during the cold winter months, if we can manage it. But ultimately, farming is a business, and it's all about return on investment. And we focus our efforts on looking at return on investment of inputs, on equipment, increasingly on logistics. And we have growing pressures on the farm. We're needing to increase our yield. We've got increasing input costs. We've got land, power, machinery costs that are increasing, not to mention the cost of land. Perhaps the biggest pressure for us to maximize our yield is actually coming from Coffee Row. But does Coffee Row or maximizing yield necessarily provide maximizing benefit? So we'll drill into that a little bit. So what is currently possible? So Tim Lamyman actually broke 2 world records in 2022. He grew world record wheat yield and barley yield. The variety that he grew was DSD Champion, and he grew 267 bushels an acre wheat. Now that happened to be a feed winter wheat with quality characteristics that are a little bit below what we accomplish here in the prairies. But what was the agronomy package that he used to grow that crop? Well, first of all, the crop was seeded in September at 134 pounds per acre. He had 3 nitrogen applications of a little over 90 pounds per acre each application. There were a total of 10 different products used in his fungicide and herbicide applications, and there was indications of 2 biological products were used in that package. Now he also, as I read the details about the crop, it was mentioned that the crop had tillered to 600 to 650 heads per meter squared by February. So obviously that is not anywhere around here. Where did that occur? Well, it was in Lancashire, or Louth, Lancashire. It's located off the east, or on the east coast of England. The type of soil that the crop, or the type of soil that's common in the area is the Holderness Association. It's a loam to clay loam soil with a pH of 7 to 8 and a clay content of 25 to 30%. The type of growing season that is occurring at Louth, well, it's very different than here. It doesn't get very cold, and it doesn't get very hot. It actually doesn't even freeze, but the growing degree day accumulation is pretty slow through December, January, and February. When it comes to the rain that they get, well, it is England, and we know that they get a lot of rain there from the time of seeding to the time of harvest. 10 months of that crop building yield potential, there's on average about 24 inches of rain in that part of the world. The write-up indicated that that world record crop it was a little bit of a drier year, but I couldn't get the details to share with you, but on average, they get about 24 inches of rain. Now that's a little bit different than what we have here in the prairies, and I just used Brandon as an example. We have a short growing season. We have our 100-day crops. The 30-year average for the rain that we get is about 8 inches of rain for May, June, July. And if we think about it, for the bushels that Tim was able to generate for the record crop, relative to the bushels that we grow here on the prairies, bushels per inch of rain, we're doing pretty good. Now, Tim's record wheat was 267 bushels an acre. The 5-year average in England is only 120. So relative to what we're doing on the prairies with our 100-day crops, we're doing pretty good. So just to drill in, or I guess as I was describing that record crop and the circumstances of what Tim did to grow that crop, I imagine you were thinking about, well, how does that relate to my farm? In essence, you were applying that information to your mental model about growing wheat on your farm. So let's drill into that a little bit deeper. First things off, let's let that go. The first thing that we want to think about is that what is the genetic yield potential of that crop? And of course, that crop has to be pertinent to the environment that we're growing in. The next considerations are the moisture, the temperature, the light quality and quantity that we have to grow that. The next consideration is the soil that we have on the farm to grow yield. And soil texture and soil salinity has an impact on the moisture available to grow that crop. Soil texture and soil pH also has an impact on how nutrient supply is available to that crop. And soil salinity has an impact on the compaction and root surface, how the roots can grow through that soil. So agriculture research has been looking at the different aspects of the factors impacting crop growth and crop yield. Been doing that for well over 100 years. But somebody who had a lot of influential research was this individual, Dr. Stan Barber, a fellow who originates from Wolseley, Saskatchewan. And when he was doing his master's research at the University of Saskatchewan back in 1947, it was his research that was the first in the world that used radiolabel phosphate in a fertilizer trial. And that black and white image in the top right-hand corner of the picture is actually a picture of a wheat plant showing where the radioactive phosphate had accumulated in that plant. Now, Dr. Barber continued his education, taking his PhD at the University of Missouri, and then had a career of research and teaching at Purdue University. And for over 30 years, he was investigating the mechanism of nutrient movement, the nutrient flux in the soil, and because they're able to observe nutrient movement in the soil, because they're able to observe nutrient movement in the soil, they're able to measure it. And they started to measure that under different circumstances. And by repeating the studies, they're able to see, well, how does the soil move from the soil toward and into a plant root and up into the plant? Now, this research was very, very difficult to do and is even harder to implement because of the limitations of conventional soil testing. But that research was summarized to create a textbook that the graduate classes of soil fertility look at. It's first published in 1995 and reprinted in 2017. And it is this research that is the basis of the technology that I've had the privilege of using for 25 years in my consulting career. And that technology is the PRS technology. Now, PRS technology has got two components. The soil analysis uses a plant root simulator probe, a technology developed at the University of Saskatchewan. It is an ion exchange resin membrane that, when placed into the soil, it measures the bioavailable or the plant available nutrient supply to that crop. I've started an animated video here to show how that works. So what was added there was water, A warm, moist soil becomes biologically and chemically active, and as the nutrients start to cycle off the clay and off the organic matter, a plant does not care where that nutrient comes from. As long as the nutrient moves into soil solution, it's going to be available to the plant. So this is fundamentally a different type of measurement than a conventional soil test that uses a chemical wash of the soil. We're measuring only the nutrients that are going to be supplied to the crop, not what's in the soil. What we like to describe this as is like getting a horsepower rating of your soil, of your nutrient supply from the soil. So in research, the PRS probes are used around the world, from the Arctic to the equator, from mountaintop to seashore and everything in between. And we're officially on all 7 continents, where the probes, this research scientists had a little bit of a challenge with the penguins, where the penguins went after the probes, were pulling them out of the ground because they were kind of puzzled as to, well, what were these probes doing, sticking out of the ground. Now for farm purposes, we collect a soil sample and we bring that into the lab, and under standardized conditions of time, temperature, and moisture, the probes are in the soil sample, and then we run the analysis on the probes. Now that data goes into a computer model called the PRS Cropcaster, and I'm just going to exit the PowerPoint here for a moment and switch over to the Cropcaster. So quickly, to give a description of what we have here, this is our main dashboard. The first thing that we consider is, well, what type of soil are we working with? Is there a compaction zone, or is there a hard pan in the soil? That's where the density value comes in. That restricts root growth in the crop. Water storage index, well, that is the texture of your soil. And you can have your sandy soils, you can have your loam, clay soils. So that's the soil characteristics. Up on top of the dashboard here, we have the growing season weather. So we have soil moisture, precipitation, and irrigation if it's available. For the rain, we as a starting point of conversation, we go to Environment Canada for the closest weather station and what's the 30-year average, and that's the start of conversation with regards to rain. Now for canola, we use maximum temperature during flowering, and we can have mild flowering conditions where we can get into years where we get a lot of heat, and we see that starts impacting yield potential. So that's the consideration for canola, or one of the yield determining factors, temperature during flowering. For pretty well all the other crops, we use growing degree days, so how warm or cold the growing season is. Soil chemistry is looked at from a pH and soil salinity perspective, and we measure that every time it's requested at the lab for the fields. And then finally, we have the nutrient supply potentials. These are the nutrients that the PRS probes are measuring. The length of the red line is like a fuel gauge. The longer the line, the greater the soil supply rate of that nutrient. Now the number above the line, this is all in farmer speak. This is pounds per acre. So we have 26 pounds of soil supply nitrogen, 12 pounds of phosphate, 61 pounds of potassium. Now for this, those supply rates, they change with the type of growing season that we have. So if we have a drier growing season, the supply rates go down. If we have a wetter growing season, the supply rates go up because the soil is more active in supplying nutrients, and the roots have an easier time growing through the soil, finding nutrients. Now these nutrient supplies, they also change with the type of crop that we're growing. And if you think about it, if you pull up a canola crop and you plant, and you pull up a wheat plant and you take a look at those roots, well, you know that those are very different rooting characteristics between those crops. Well, in the Cropcaster model, we have the rooting characteristics of 27 different crops built in. I'm just going to ask you to look at the supply rates here, and I'm going to call out the crops as I rotate between them. So this is what it looks like for canola. This is what it looks like for grain corn. Here it is for flax. Here it is for wheat. Are there any oat growers in the room? Some oat growers? Okay, so I want you to think about this. When you're growing your oats relative to spring wheat, how do you fertilize with nitrogen? Do you put on more nitrogen, the same, or less nitrogen? And most of the time, 95% of the time, farmers respond that they dial back on their nitrogen. And in Manitoba here, for the most part, it's because what we experience is lodging in the oats. In the drier parts of Saskatchewan, we just don't see a yield response. So Grandpa figured it out, then Dad was doing it, now we are. We're all dealing with the same symptoms, but nobody's talking about the why. So where wheat is seeing 26 pounds of soil supply nitrogen, I'm going to switch to the new oat varieties here. 62 pounds of soil supply nitrogen. The same soil sample, meaning different things to different crops because of the rooting characteristics of those crops. Just to finish it out, here's what it looks like for peas. This is what it looks like for soybeans. You'll see that the fuel gauges are full. This is where, although soybeans export a lot of phosphate and potassium in the seed, it is rare that you see a fertilizer response in soybeans because soybeans have such an aggressive rooting system, finding nutrients in the soil. So you'll notice in the top right-hand corner here, we got the grain bin. We got maximum yield for these soil characteristics and for this growing season scenario. For the new wheat varieties, no bugs, no disease, money's no object. There's an 88 bushel yield potential. I call that bragging rights on Coffee Row, but not necessarily you buying the next round of coffee. What we want to focus on is the yield inside the grain bin, and that's where we use your fertilizer costs and new crop price expectations to generate a yield or to look at the economics. And for the macronutrients, for nitrogen, phosphate, potassium, and sulfur, we had the yield response curves. And we basically tried to determine where on these curves do we stop investing in fertilizer? Where does the economics just not justify the investment anymore? And if you look at the curve, we have, and particular to wheat, the steep part of the curve is building yield, but as we go over the shoulder, we start building protein. This spot on the curve, well, here is about a 10.5 protein. This is about a 12.5 protein. This is a 13.5 protein, and this is a 15% protein, maxing it out. So I've got a few scenarios to compare, just looking at wheat. The first set here is using an 80 cent a pound nitrogen. Scenario A is for a 15% maximum yield. The scenario B is for a 13.5, and scenario C is for a 12.5 wheat. And I looked up from a local line company the Brandon price for December delivery hard red spring wheat. So for a maximum yield for a couple of feet of moist soil and 8 inches of rain, we have an 88 bushel yield potential, and we're applying 160 pounds of nitrogen, 48 pounds of phos, a little bit of potassium, a little bit of sulfur. It's costing us $178 an acre for maximum yield. To grow the 13.5 yield, we're doing a 120-35-07, growing 83 bushels. Now we are yielding less, but we have $50 an acre less risk, but we're only giving up $9 of income. $50 less risk for $9 less income. So there's a point in there where we're spending $1 and only getting 90 cents back. Looking at a 12.5 protein, we're down to 100 pounds of nitrogen with 35 pounds of phos, 7 pounds of sulfur. We're spending $113 an acre, so $15 less risk, but we're giving up $25 of income. Now, for some farmers, if they have a limit to their budget, well, here's the reality. But we are, in most circumstances, we would think that we're giving up too much in opportunity by pulling back to a 12.5 protein. But this is using 80 cent nitrogen. I ran the same set of scenarios using $1 a pound nitrogen, something like what we had experienced just a couple years ago. And here's the numbers. So the same blends, but now with $1 a pound nitrogen, the 15% protein, we're at $210 an acre spent, and we're earning $32, $33 an acre as a net income. The 13.5, we're spending $153 an acre. We have the 83 bushel yield. We have, in this case, $60 less risk. we're only giving up 90 cents in income. So it isn't the maximum yield that we want to be focusing on, it's maximum economic yield. And then the 12.5 protein, we've got $20 less risk, giving up 3 bushels, $20 of risk, $20 of income. Well, there's your dollar in, dollar out. And in the fall of 2021, it was quite an interesting year to do crop casting. I had customers who had bought nitrogen in the summertime, and it was 60 cents a pound nitrogen. And I had customers that bought nitrogen rather late. High water mark for me was $1.26 a pound nitrogen. Those are very different economic conversations. 60-cent nitrogen for $1 versus $1.26. We want to be focusing on what the maximum return on investment is. Just to look at canola here for a moment, for the similar soil, same growing conditions, maximum yield of 80 bushels an acre. This column right here actually is the nutrients required to grow maximum yield. If I ask the model to do a quick calculation to get a $1.50 return on the last dollar invested, we would do a blend of a 127, 34, take the potassium out, a little bit of sulfur. And that would be the economic optimum for a $1.50 return on the last dollar invested. So I could spend a lot of time looking at all kinds of scenarios. We can look at 7, 9, 11 inches of rain. What if we fertilize for 8 and only get 6? We can compare wheat to feed wheat to durum to barley to oats. That's what the cropcaster is there to do. It's if we're going to feed canola or grow canola, how do we fertilize canola? If we're going to grow a cereal, which cereal is going to have the best economic response? And if we have a risk tolerance, well, how do we spend a specific budget? So I'm just going to exit the cropcaster here for a moment and get back to the PowerPoint. And I do want to talk about how weather has been having an impact on soil nitrogen supply potential. Now, to put a little bit of context around the data that I'm going to show you, Western Ag has its greatest footprint in Manitoba on the west side of the province. So the majority of the data that I'm going to present to you is coming from that data set. In Saskatchewan, I've got it divided into the southeast and northeast Saskatchewan. Where the line is for any of those here from Saskatchewan, it's the Qu'Appelle Valley, and north, that's what's considered northeast Saskatchewan. Now, I also want to talk about the growing seasons because it has a big influence on what we see in our soil analysis. The top row is comparing the summer season that's influencing yield potential, so May, June, July, and the bottom row is showing the fall, the August, September, October. And beginning in 2019, we had a pretty good growing season, had good moisture, generally speaking. And then, I am sorry to bring it up, the fall of 2019, the harvest from hell. I know a lot of us have been trying to suppress that because of the challenges that we had in that fall. But that fall had, I use it as a benchmark year for the nitrogen supply potentials that we saw. Now, the wet fall of 2019, that stored moisture actually helped us grow still some pretty good crops in growing season 2020. The fall of 2020 was a very dry fall. At my farm in Alameda, we didn't have any moisture from the end of July all the way to freeze up. So a very dry fall, a total opposite of 2019. For 2020, that dry fall in 2020 continued on into the drought year of 21. For those of us farming in 21, well, we can empathize with our grandparents with the drought of 1961 and with our dads with the drought of 1988. They are comparing, it's a similar type of drought. Now, starting the third week of August, we started to receive rain in the prairies, and in some areas quite a lot of rain. And that resulted in some very interesting changes in the soil that I'll talk about in a moment. The moisture from the fall of 21 continued on into the spring of 22, growing season 22, and then we had another dry year in the fall of 22. That dry fall of 22 carried on into the growing season of 23, and then in some regions we started getting some moisture. So let's talk about what were we seeing for nitrogen supply potentials as a result of those years. So starting off with nitrogen, or with Manitoba, and this is a frequency graph. So it's showing what percentage of samples that we received under different nitrogen supply rates. And so in essence, it's what percentage of fields were in low nitrogen supply, medium supply versus high nitrogen supply. And incidentally, where we start making nitrogen recommendations is anything to the left of the gold circle on the graph. Now 2019 is the silver bar on the far left. And with the 10, 15, 20 inches of rain that we received, or even more, Manitoba had the snowstorm at Thanksgiving. We had saturated, leaching, we had denitrification, we had a saturated soil, that there was no mineralization happening. So it's little surprise that we have a lot of fields that are low in nitrogen supply potential. The fall of 2020 was a dry fall. Our analysis started seeing a nitrogen mineralization burst present in the soil. Because Western Ag customers were seeing this nitrogen for about 30% of the fields that we sampled, there's a higher nitrogen supply. We didn't have as much nitrogen in the soil in the drought year of 21, so we didn't see, as big a burst. How did that jump ahead so fast? We didn't see as much nitrogen in the soil following the drought. Now, to be fair, Western Manitoba also did not experience the same degree of drought as other parts of the prairies. So that's a consideration in the data set as well. Now, fall of 22 was dry, fall of 23 was even drier, and so 64% of fields in Western Manitoba were short of nitrogen. Or to say it another way, 36% of fields have enough nitrogen to carry that crop. This is what it looked like in northeast Saskatchewan, 2019, again far left, the silver lines, we had the wet year. The dry fall of 2020, now it was a little bit more, I'll call it average for northeast Saskatchewan in fall of 2020, but then we had the drought year of 21, and we had in northeast Saskatchewan, that's where the greatest amount of organic matter is in the province of Saskatchewan. That's where we have the most organic matter in our soils, and we saw an explosion of nitrogen potential, supply potential, after the drought of 21. Then we had the dry fall of 22 and then 23. Jumping into southeast Saskatchewan, similar pattern. The wet fall of 2019. Then we had the dry fall of 2020, the drought year of 21, dry fall of 22, dry fall of 23. So what is going on in the soils? What are we seeing? Well, when soils go through an extended period of drying, there's physical and biological changes that occur in the soil. And this results in a buildup of a nitrogen mineralization potential. Now, in the scientific literature, they talk about this as being a drought-induced nitrogen mineralization burst, bit of a mouthful. They've been nicknaming it the Birch effect. And just to talk about that a little bit more, I'm going to zoom in on this graph. The way I think about the mineralization potential is like a soil, the mineralization potential being like a rubber band. And every week of dry conditions that you have, and if you look on the bottom right-hand side of the graph, there's your weeks of dry conditions. Every week of dry is putting another wrap on that rubber band. And the amount of potential that builds up in that rubber band relates to the amount of organic carbon that you have in the soil. If you multiply by 1.7, you get the approximate organic matter content of the soil. So every week of dry is putting wraps on. The amount of potential that's in that rubber band is the amount of organic matter that's in the soil. Now, I feel southwest Saskatchewan has the Birch effect happening almost every year. They're always dry in southwest Saskatchewan. So we got lots of wraps on that rubber band, but when they get some rain and that potential releases, well, there isn't much of a burst because there isn't that much organic matter in the soil to release the nitrogen potential. But as we get into the dark brown soils and into the black soils, we have a thicker and thicker, heavier rubber band. You have your weeks of dry, the fall of 2020, 3, 6, 9 weeks, 12 weeks. of potential. The fall of 2020, we went into freeze-up, dry. That potential stayed there till springtime. All we needed was a warm soil and the spring melt, and the soil exploded with mineralization potential. And that's what we saw with the PRS analysis. So how do we see this in the scientific literature? Well, a recently published article. Now this is actually work done in Switzerland. They used perennial ryegrass in the research, and they had their research plots, and they induced drought on some of the plots. The way they did that is that they applied rain shelters. So they had rain-fed plots, and then they had drought plots. The rain shelters were on for 2 months. Then they took the shelters off and they irrigated the plots to get everything up to the same moisture. And they had another treatment in there. They had with and without fertilization. Now, with regards to fertilization, they didn't apply very much fertilizer. It was only about 12 pounds of nitrogen per acre. But then they applied installed the PRS probes in the plots, and we're seeing the nitrogen, the plant available nitrogen supply over 27 days. And we're seeing the birch effect happening in these plots. In the fields that had the drought and then were wetted up, with and without fertilizer, we had a nitrogen mineralization burst happening. And where there was a little bit of fertilizer, it's just remarkable how much more mineralization happened. Now, the researchers continued this work, looking at doing a dry matter yield, and the yields mirror what the nitrogen supply measured. So the PRS probes are not measuring an artifact, they're actually measuring the plant available nitrogen supply. So for our lab, when we have a dry fall, we check all the soil samples for moisture content, and when they fall below a certain threshold, we implement a pre-wetting protocol. Basically, the samples come in, they're moistened part-way to field capacity, and then the soils are put into a fridge for 2 days. Then they're pulled out. The PRS probes are installed for 24 hours, which is our standard protocol. And then we analyze the data. So what does that look like in the cropcaster? Well, using our standard protocol, and this is a field I had sampled near Weyburn. If we just brought the soil in, moistened the sample, put the PRS probes in for 24 hours and pulled them, we would have about 21 pounds of soil supply nitrogen available to that crop. Using the pre-wetting protocol, 85 pounds of soil supply nitrogen, 4 times the nitrogen supply potential for the circumstances of this field. So what does that mean for farmers? So this is an example from a customer from north of Saskatoon. The soil was sampled in the fall of 2021, so after the drought year. And so if you see the nitrogen fuel gauge there, it is full. It's actually beyond full. We're seeing a nitrogen supply potential of 210 pounds of nitrogen. My colleagues were trying to convince the farmer that you don't need any nitrogen, you just need a little bit of phosphate for this crop. Now the farmer took that advice, but some farmer psychology came into effect. And if you notice in the picture, there is a highway and there is a town. And is a farmer going to put no nitrogen on a field that's along the highway close to town? It's pretty rare. Pretty rare. So this is what the farmer did. He did a just-in-case management. He applied 80 pounds of nitrogen with 30 pounds of phos as a blend. Now, because it was a blend, if we wanted to do a comparison, it was either no fertilizer or the blend. So the farmer was willing to do a couple of strips of no fertilizer. And then my colleagues went back and they went and looked at his yield data. And they took 5 strips of yield before, 2 untreated strips, unfertilized strips, and 5 strips after. And this is what the data showed. You'll notice that in every instant, the fertilized strips yielded less than the untreated fertilizer. Now, if we use $1 a pound nitrogen, as it was at the time, that's $80 an acre. The average yield reduction is a little bit over 8 bushels an acre. This farmer's net income was reduced by $160 an acre. Not to mention the environmental loading of having that excess nitrogen in the soil. So what was happening? So we had the 210 pounds of soil supply nitrogen that the cropcaster, the PRS analysis was predicting. We added another 80 pounds of nitrogen. So we had a total of 290 pounds of nitrogen for that crop. A maximum yield of an 89 bushel crop only needs 190 pounds of nitrogen. We were 100 pounds of nitrogen beyond the maximum required for a 90 bushel crop. Clearly, we were onto the backside of the nitrogen curve. Each additional pound of nitrogen was taking away from yield. So the federal government has its aspirations to reduce greenhouse gas emissions from our fertilizer applications. And industry and academia are really encouraging us to be better stewards of the fertilizers that we apply to the land. And they're using a program, the 4R Nutrient Stewardship Program, where they focus on, as we apply or consider using our fertilizers, that we have the right rate, the right source at the right rate, at the right time, at the right place. From my perspective, the most important, the most influential consideration in the 4R nutrient stewardship is to be using the right rate. Now, to summarize, for us to have successful, sustainable farms, it requires a focus on profitable return on investment. Understanding the constraints to yield potential will help you optimize your fertilizer investments. PRS technology measures bioavailable nutrient supply, focuses on maximum economic yield, and tailors fertilizer plans to your farm. Weather cycles have an impact on soil nutrient supply potential. Understanding that potential improves our efforts in stewardship and profitability. And with that, I'll conclude my presentation and invite any questions or discussion. Questions? So the question, if I heard it correctly, is how does frozen soil influence the birch effect? So as soils cool down and transition into freezing, well, the biological activity is stopped. So in the fall of 2020, that was stored potential. Nothing was happening. That potential remained there to the following spring and was triggered with the warming of the soil and the moisture. Now, I was a little bit concerned in the fall of 21 because, if you recall from the weather graphs, we had rain in the third week of August. We had a drought, many weeks, putting wraps on that rubber band, and then we had the rain in the third week of August, and the mineralization burst happened in the field. Now, anecdotally, I had heard comments where farmers are saying with their conventional soil test, and guys chased their agronomists out to get sampling in the fall of 21 because every week the price of nitrogen was going up and up and up. I just had a drought. I need to know what's in the soil so I know what to buy. Well, they had more nitrogen in the soil than what they had applied in the spring. And well, how did that happen? Well, in the fall of 20, with the conventional soil test, the fall of 20 again was a very dry fall, no moisture, was no biological activity, no mineralization, there's no nitrate to measure. So in the fall of 2020, the soil was very low in nitrogen. They applied their fertilizer, but they didn't account for the nitrogen mineralization burst that was ready to go. And so that was what was happening in the fall of 21. But that's now nitrate in the soil. And if we would have had a fall like 2019, that nitrogen would have been vulnerable. We would have lost that. Any other questions? Sorry?
You were talking about applied nitrogen helping the birch effect. Could you just talk a little bit more about that, like on drought falls, applying it a little bit, or how do you determine that?
So if I understood the question, how does applied nitrogen influence the birch effect? Does that sum it up? How does applied nitrogen influence the birch effect? And I'm wondering, are you thinking about that Swiss study where it triggered a little bit more? To be honest, I don't have a deep understanding on that process, but what I think was happening was that little bit of extra nitrogen was encouraging a quicker turnaround, and encouraging the biological activity to kickstart. And that was a bit of a synergistic effect, a catalyst to encourage more biological activity that created more of a mineralization burst. But that's about as far as I can go, the nuance of having the extra nitrogen around. But in our farming practices where we are applying fertilizer, a normal course of business, we do have more nitrogen in the environment compared to under a grassland. And so it doesn't surprise me that there can be this little bit more of an explosion in nitrogen supply potential. Any other questions? Right here.
Yeah, how do we utilize the probes if we have a zone manager typically like 3 to 5 zones?
Right. The question is, how would the PRS probes be used in variable rate fertilizer management? So so I guess to emphasize, the PRS probes are not used in the field for farm planning. The probes are used in the lab under standardized conditions, but we soil sample the field. But if you're either the dominant zone doing a composite sample or you're doing zone sampling, so each zone would be its own field, so to speak. So if you have 4 zones in the field, would have 4 samples for that, and we would crop cast each zone for its characteristics, for its slope position and the moisture related to the low slope versus mid slope, the knoll, your saline areas. We just do a crop cast for each of those, and then the process would be, well, what is the economic benefit for changing the blend between those circumstances? That's how we use the technology for variable rate. Any other questions? I appreciate your joining in this morning. With the PRS analysis and having the opportunity to see that extra mineralization burst that is there, there can be 20, 40, 80 pounds additional nitrogen supply potential that we really need to be paying attention to, not only for our economics, but also to be good stewards of the environment. Thank you for your time.